Okay, let's go ahead and start. Does anybody have any questions before I begin? So remember, at the end of class last time, I asked you to finish up that problem that we worked in class, all right? And how many of you had a chance to do that? So I put up the answers, and I'll quickly go through the solution, all right? And I want you to make sure that you have the same answer. So if you guys remember, last time we said that whenever, if possible, there are situations where you will encounter problems where the algebraic equation is very difficult to solve. And so if you want to keep it simple, if you can make appropriate approximations, then it makes the solution much easier. And so last time we looked at an example where if we were just to follow the general format in which we solve these problems, you'd end up with an algebraic expression that is very difficult to solve. And so what we do is we come up with a very clever strategy, and that is that we're going to make the reaction proceed 100% in the reverse direction. So we made it go 100% in that direction, and when we do that, that's just a regular limiting reagent problem, where you're going to have one reactant that's limiting and one reactant that's in excess. And so you just treat it like any other limiting reagent problem, and you can see that Cl2 is limiting, NO is in excess. So if you look at the ratio in which they react, it's a 1 to 2. So for every 1 mole of this that's consumed, you only need 2 of these, all right? But in reality, we have 3. So if only 2 of these are used up, you'll see that 1 is left over. And then for every 1 of Cl2 that reacts with every 2 moles of NO2, you end up with 2 moles of NOCl. So what we do is we make it go 100% towards the left. And now what we have is the reaction gone to completion that way, and now we're going to let it go to equilibrium. And so we say if it's now proceeding in the forward direction, the amount that would be consumed would be negative 2x plus 2x, and x would be formed. Okay? And so you solve for it, and we said now when we make the reaction go in the forward direction, we know that this reaction is going to react to a very small extent. And remember, we looked at this picture last time, and we said that if we start with only products and we let it go to equilibrium, the amount that is used up of the products that's used up as it goes to reactants will be really large. And so you can't make any approximations. But if we make it go 100% this way, and then make it go in the forward direction, now the amount of reactants that's consumed is going to be really small, because this is where the equilibrium constant is. This is where, when equilibrium is established, we know it's going to have lots of, it only reacts to a small extent, so it's going to have lots of reactants and very little product being formed. Okay? And that's why now we can make these approximations. We can say 1 plus 2x is 1, 2 minus 2x is approximately equal to 2. You can solve that, and now we figured out that x is 6.4 times 10 to the negative 5. Okay? Now we said once you do that, you always have to go back and recheck your assumption. Is that approximation indeed valid? Okay, and the way we check it is we say that approximation is what? 2x is small compared to 1. And we said 2x is small compared to 2. Obviously, we just need to do it once, because if 2x is compared to 1 is small, we know that 2x is going to be small compared to 2. So you can do a quick check of validation, 2x over 1 times 100. That gives you 0.0128%. So you know that this is well below our 5% threshold. All right? And therefore, we know that this approximation is valid. And so now we can say NOCl is 2 minus 2x. And you can see this number is so small compared to this that its concentration hardly changes. You can neglect the small amount. If you look at the concentration of NO, it's 1 plus 2x. If you take 1 and add this really small number to that, it hardly makes a difference within the significant figures. And then Cl2 would be 6.4 times 10 to the negative 5. All right? Now, one of the things that you may have to do sometimes is you'll be asked to calculate percent decomposition. So you've seen problems where you're asked to calculate percent decomposition or percent of reactant consumed. All right? So very often you're asked to calculate percent decomposition. And this is from the point of view of the reactant, because it's the reactant that's consumed or used up or decomposed. Okay? So whenever you calculate percent decomposition, it's the amount that decomposes or the amount that is consumed. So in this reaction, what is the amount? So let's go back and look at this. When you look at this reaction, what is the amount of reactant that's consumed? Tell me. What is the amount of the reactant that's consumed? What do you think? 2x. All right? So 2x is the amount of reactant that's consumed. So we want to calculate what percentage of of the reactant is consumed. So how would you calculate if 2x is the amount that's consumed and the amount that we started with was 2 molar? So if we say the amount of reactant that was consumed, percent consumed would be what? 2x divided by 2 times 100. Did you get it? All right? So in this case, if you wanted to, now this is not a very good problem to apply it because you're actually starting with this. All right? So let's presume that in this problem that you actually started with this. All right? This is what you started with. Your percent decomposition would be 2x divided by 2 times 100. Got it? This is going to become important later on because when we start looking at the next topic, we're going to have to calculate percent decomposition often, and I'll come back to that and repeat that once again. Okay, so today we're going to move on to the next topic, and we're going to look at acid and base equilibria. Whoops. So today's topic, we'll be looking at acid-base equilibria, and now we move on to chapter 11 of your textbook. Okay? So we're going to start looking at acids and bases, and in our popular culture, we use the words acids and bases quite often. As all of you know, we say vinegar is acidic, we say that lemon juice is acidic, and certain drain cleaners are said to be caustic or basic. So acids and bases are very common in our everyday life. Now, if we want to really understand how acids and bases behave, we have to start with how do you define an acid or a base. And so we're going to go back in history, and sort of the earliest definition for an acid or a base comes from Arrhenius. And so we call this the Arrhenius definition. And what Arrhenius said was an acid is any substance that produces hydrogen ions. All right, and hydrogen ions, as all of you know, are H+ ions, or we also call them protons. All right? So an acid is any substance that produces hydrogen ions, and a base, hydrogen ions when dissolved in water. So it has to be dissolved in water. So when dissolved in water, and a base is any substance that produces OH- or hydroxide ions, and this would be OH ions when dissolved in water. All right, so the Arrhenius definition is that an acid is any substances that produces H plus ions or hydrogen ions when dissolved in water. And a base is any substance that produces OH minus ions when dissolved in water. So an example would be, for an acid, would be things like HCl, all right, when this is dissolved in water. So it's HCl dissolved in water, aqueous. Things like nitric acid dissolved in water. This is acetic acid when it's dissolved in water, all right? And a base would be anything that produces OH minus ions, something like NaOH, aqueous, calcium hydroxide, aqueous, cesium hydroxide, aqueous. These are all examples of Arrhenius acids and Arrhenius bases. Okay, now let's go back and look at the definition. Arrhenius definition tells us that an acid is any substance that produces H plus ions. So if you take an H plus ion, we also call it a proton, because let's go back to the first quarter when we looked at atomic structure. And if you take the hydrogen atom, the description of a hydrogen atom is that it has an atomic number of 1. When it says it has an atomic number of 1, what does that mean? What does atomic number give you? Number of protons. So it's got 1 proton. It has a mass number of 1. What does mass number give you? Protons plus neutrons. So the end result is what? If you take the nucleus of the hydrogen atom, what is left there? Just 1 proton, because the atomic number is 1 and the mass number is 1. So if you look at the nucleus has 1 proton, all right? And we know that if you know what the atom is electrically neutral, so if the hydrogen atom has 1 proton, what do we know about the number of electrons? 1 electron. So in H plus, we take away this electron. All right, so if you take the hydrogen atom, it's got a proton and an electron. All right, now if it's H plus and you take that electron away, what are you left with? A proton. So that's why sometimes H plus ions are also called protons, just because of that. All right, and so from now onwards, to describe hydrogen ions, we'll use the word proton quite often. And we use the word proton loosely. All right, the term proton describes the subatomic particle proton. It also describes the hydrogen ion. And so when we talk about acid-base chemistry and we use the word proton, we're using it under this context. All right? So we say that an acid produces protons. So if I take HCl, and when you dissolve HCl in water, what you end up with is H plus ions and Cl minus ions, and therefore it's an acid. So according to Arrhenius definition, you dissolve HCl in water. When it's dissolved in water, it produces H plus ions, and therefore it's an acid. If you take something, so this is an acid. If you take something like NaOH, now, can everybody see that HCl is a covalent compound? All right? It's a polar covalent compound because there is a covalent bond between hydrogen and chlorine. Now, if you take sodium hydroxide, what kind of compound is that? It's got a metal, cation, Na+, and it's got a polyatomic anion, which is hydroxide. So when you have cations and anions, what kind of compounds do you form? Ionic compounds. So sodium hydroxide is an ionic compound. It's a giant lattice structure. It's a crystalline solid. But the moment you put it in water, this whole giant extended three-dimensional structure just disintegrates completely, and it forms Na plus ions and Cl minus ions. So the lattice structure completely breaks apart, and it dissolves completely in water, and it produces. So when you dissolve sodium hydroxide in water, what you end up with is Na plus aqueous plus OH minus aqueous. And because the moment this whole ionic compound dissolves in water, now you have hydroxide ions being produced. Now the lattice structure, it's no longer held together by electrostatic attractions. This giant structure falls apart and it dissolves in water. All right? And so here you're producing hydroxide ions, and therefore this will be a base. All right? But unfortunately, the Arrhenius base is very limiting because, as all of you can see, when we use this Arrhenius definition, we're limited by the fact that the solvent has to be water. Solvent is a dissolving medium, all right? And so you always have to dissolve something in water for it to act as an acid or base. And what we need is we need a broader definition. We need to encompass substances that don't always include water, all right? And so a much broader definition for acids and bases are the Bronsted Lowry definition. So we go to the Bronsted Lowry definition. And from now onwards, we're always going to refer to this definition because it encompasses a broader class of compounds. All right? It includes substances that don't necessarily have to dissolve in water. Okay? So we start with the Bronsted Lowry definition. And according to the Bronsted Lowry definition, an acid is any substance that can donate, all right, a hydrogen ion or protons, and a base is any substance that can accept a hydrogen ion or proton. All right? So now we look at the Bronsted-Lowry definition. According to the Bronsted-Lowry definition, an acid is any substance that can donate hydrogen ions or protons, and a base is any substance that can accept hydrogen ions or protons. So an easy way to remember this is an acid, we call an acid a proton donor, and a base is a proton acceptor. So from now onwards, the criterion we're going to use to decide whether a substance is an acid or a base is we're going to say an acid is a proton donor. So if the substance donates a proton, it's an acid. If a substance accepts a proton, we're going to call it a base. So an easy way to remember it is proton donor, an acid, proton acceptor, a base. All right? So let's take an example of a Bronsted-Lowry acid and a base. Okay? So let's take the example of HCl. So let's say we have HCl in water. So if I draw the Lewis structure of water, this is what it looks like. In water, if I have HCl, so both of these are covalent compounds, and if I draw the Lewis structure for both, this is what it would look like. Okay? So now in water, what happens is that the HCl will give up an H plus ion. So remember, this is a covalent bond. And the covalent bond is made up by sharing a pair of electrons. The hydrogen atom donates an electron. Chlorine has 7 valence electrons, so there's 1 electron in chlorine that's given to the pot, and it's that the pair of electrons are mutually shared between the two. But when you form an H plus ion, what happens is both electrons that belong to this bond go to chlorine. And so what happens is hydrogen leaves with no electrons at all. That's why it's H plus, all right? And so the H plus ion combines with this to give you, we call this a hydronium ion plus Cl minus, because now chlorine, remember chlorine starts off with 7 valence electrons and it's sharing a pair of electrons. It's sharing that electron with hydrogen. Now, when chlorine leaves, it takes its 7 electrons and also takes the hydrogen's electrons. So now it has 8 electrons, and therefore it's Cl minus. And we're left with hydronium ion. Okay? Now, it's important to remember that In the Arrhenius definition, we said it produces H plus ions. All right? In reality, if you're in water, it's important to remember that in water, H plus ions do not exist on their own. Okay? Strictly speaking, if you're in water, you can't have H plus ions on their own because the H plus ion actually sticks to a molecule of water and it gives you a hydronium ion. So in fact, this is a better description rather than the Arrhenius where we just say it produces H plus ions and we say H plus ions in water. In reality, strictly speaking, H plus ions do not exist alone as discrete entities in water. They're going to combine with the molecule of water to give you a hydronium ion. But in fact, this is not the best description either, because as all of you know, if you're in water and you have a hydronium ion, you can figure out what the shape looks like. If you look at this, it's got lone pair and 3 bond pairs. The steric number is 4. All right, so if you look at the shape of this molecule, this is what it looks like. It has a tetrahedral electron geometry. So you have oxygen with a hydrogen like that, and like that. There's a lone pair there. All right? So its electron geometry is tetrahedral, but its shape is actually trigonal pyramid. So the shape of this molecule is trigonal pyramid. All right? And if you look at this in water, as all of you know, water forms hydrogen bonds. So even though we describe hydronium ion like this, in reality, this is not the best description of the hydronium ion because this hydronium ion is going to hydrogen bond with other water molecules like this. Remember, so each of these hydrogens can act as a hydrogen atom donor to form a hydrogen bond with another water molecule. The oxygen has 1 lone pair and it can act as a hydrogen bond, hydrogen atom acceptor, and so it can form this hydrogen bonding interaction. And even this is not a good description because now if you look at all those water molecules surrounding that, they can form hydrogen bonds as well. So actually, the structure is an enormous structure of the hydronium ion hydrogen bonded to water molecules and those water molecules forming hydrogen bonded to other water molecules. And so if you want to have a really true description of a hydronium ion, it's a cluster of all of these entities together. Does that make sense to everybody? But for convenience, we're going to just write it down as hydronium ion. All right? And so we're going to call this the hydronium ion. All right? So essentially what's happening here is that you can see that this covalent bond is broken, and this HCl donates a hydrogen atom to water, all right? And it forms a Cl minus. So if I want to write it in terms of the formula, I can say HCl, when we dissolve that in water, we're in liquid water, and that gives me hydronium ions. And when I put in parentheses aqueous, this is the structure that I'm talking about, okay? Plus Cl minus aqueous. So now let's so what we've written down is the interaction of HCl with water to give you hydronium ion and chloride ions, all right? Now we want to apply the principles that we've learned, the definition that we learned from Bronsted, Lowry definitions. Okay? So if I turn to HCl, can everybody see that in this interaction, HCl is the proton donor. So this is the proton donor. And we know if it's a proton donor, what do we call it? An acid. Now if I turn to water, can everybody see that in this interaction, who's accepting the proton? When the proton's given off, who's picking up that proton? It's water. So that means the proton here, this is the proton acceptor, and therefore this would be the base. All right? Now again, remember these are examples of equilibria. So we see a reversible arrow there. And if it's an example of an equilibrium and there's a reversible error, what does that tell you? That you have both the forward reaction taking place and you have a reverse reaction taking place as well. So for the forward reaction, you can see that HCl is the acid because it's the proton donor. Water is the proton acceptor, therefore it is the base. Now let's turn to the reverse reaction. If you look at the reverse reaction, can you see that if these two were the reactants, now this would be the proton donor, and this would be the proton acceptor. And therefore, for the reverse reaction, this would be the acid, and this would be the base. Now, since for the forward reaction, the term acid is already taken, what we say is we call this the conjugate acid, and we call this the conjugate base. All right, so for the reverse reaction, we call the acid the conjugate acid, and the Cl minus for the reverse reaction is called the conjugate base. All right, now we use this term conjugate acid, and so if you look at this, we call this, if you look at these two, this is a pair, this is the base, and we call this, if H2O picks up a hydrogen, it becomes H3O plus, and we call that its conjugate acid. And then we take this acid and we pair it up with HCl, and you can see that HCl has a proton. Cl minus is when it loses the proton. All right? And so we call these conjugate acid-base pairs. So there are two conjugate acid-base pairs. And so we call these conjugate acid-base pairs. And they are defined as a pair. So the conjugate acid-base pairs consist of two substances related to each other in the donation and acceptance of a proton. All right, so we're looking at conjugate acid-base pairs, and a conjugate acid-base pair is two substances that are related to each other. The only difference is one of those will have a proton, the other would have lost that proton. All right, so examples would be, so we look at HCl. So if I take HCl, this is the acid form. It has a hydrogen. If it loses that hydrogen, it becomes Cl minus. So what we do is we use a diagonal line and we put these pairs together, and you can see the only difference between the two is one has the proton, the other has lost the proton. So it's the difference between donating or accepting a proton. And we call this a conjugate acid-base pair. So if you look at water, the acid form of the water in that equation is H3O plus. So H3O plus and H2O are conjugate acid-base pairs as well. All right? So I want to remind you that if this is what we're looking at, if HCl is what we're looking at, we call this the acid, and Cl minus would be the base form, so it's called its conjugate base. Now, if I want to focus on Cl minus, and I say Cl minus is the base, then what you say is HCl is its conjugate acid. So the word conjugate, these are pairs, and I would like them to a married couple. All right, so they always come as pairs, they're husband and wives. All right? Now, if we're talking about the husband, what do we call the wife? The spouse. So if we're considering the husband, then the wife would be the spouse. If we're not interested in the husband, we're talking about the wife, then the husband is the spouse of that wife. Do you understand that? So the word spouse is used to describe the other half of the couple. It's the same thing here. So we call them a conjugate acid-base pair. If we're talking about the acid, then the base would be its conjugate base. If we're talking about the base, then the acid would be its conjugate acid. And we say they're conjugate to one another. Did you get it? So they go as pairs, and these are called conjugate acid-base pairs. So one of the take-home messages when you're studying tonight is that whenever you look at examples, you should be able to identify what the conjugate acid-base pairs are. All right? So if I write a general reaction, so for a general reaction for any acid, so for a general reaction, we can say the acid is HA. So the acid has to have a proton. All right? And so in water, if you dissolve the acid in water, this is in liquid water, then you would establish the equilibrium where you have hydronium ions plus A minus. All right? So this is the general form of any reaction where an acid is HA. All right? Now keep in mind that any compound that has a hydrogen will not act as an acid. All right? It has to be a class of compounds that are called acids. So it's very, very important that you remember that not every substance that has hydrogen atoms will act as an acid. All right? There is a class of compounds that are good proton donors that donate protons. And if they donate protons, then they're called acids. All right? So in this case, we're going to take the general class and we're going to call them HA. So this would be the acid. This would be the base. This would be the conjugate acid for the reverse reaction. And this would be the conjugate base. So if you want to look at the conjugate acid-base pairs, in this, you have two conjugate acid-base pairs. The acid form is HA, and its conjugate base would be A minus. And then for the second one, the acid form would be H3O plus, and its conjugate base would be H2O. All right? Now, this is an equilibrium. So if it is an equilibrium, then we can write an equilibrium expression, or the law of mass action. And so for this equilibrium, we can say Ka. So we call this equilibrium constant Ka. And Ka means it's called the acid dissociation constant. All right, so this equilibrium constant is called the acid dissociation constant. And to distinguish it from Kc or Kp, we give it a subscript A because this describes a class of reactions. All right? And Ka equals the concentrations of the products all right, divided by the concentrations of the reactants. But now if you look at this, water is pure water, pure liquid as a reactant, all right? And it's also the solvent. So we know that when you have reactions where you have pure liquids or pure solids, or if something is a solvent, we know that their concentration does not change. And therefore the concentration of pure water is a constant. And we move all the constants onto one side. So the concentration of water is already incorporated into this equilibrium constant. And so this would describe the law of mass action, or the expression for the chemical equilibrium that we're looking at. Does that make sense to everybody? Now, water is in such large amounts. Remember, it's a solvent. The water is in such large amounts that its concentration does not change. Now, I'm going to give you an exercise. If I asked you to calculate the concentration of water, can you do that right now? What is the concentration of water? So you have pure water. What is the concentration of pure water? So if I throw a question like that, how do you start solving it? Initially, you look at it and your eyes go wide, like, how can I calculate the concentration of water? I don't have any information. So if I ask you to calculate the concentration of water, what should your first question be? What is the definition of concentration? What is the definition of concentration? Moles divided by the volume. The unit of volume has to be what? Liter. All right? So if I want to calculate the concentration of water, I need to pick a volume of water. Pick a volume of water. 1 liter. All right? So if I want to know 1 liter, can I figure out how many moles are there in 1 liter? Yes or no? How do I do that? What is the definition of mole? So always go back and ask yourself. So we started with the definition of concentration, moles divided by volume. We pick 1 liter. Now I need to figure out the moles in 1 liter. So what is the definition of moles? It is mass of the 1 liter of water divided by what? Molar mass. So what is the mass of 1 liter of water? What do we know about water? Its density is what? 1. So it's 1 gram per milliliter. 1 liter has how many milliliters? 1,000. So if you have 1,000 milliliters, what is the mass of 1,000 milliliters? 1,000 grams. Calculate the moles in 1,000 grams. Anybody got a calculator? So what is the molar mass of water? This is something that you should do back of the envelope. What is the molar mass of water? 18. Oxygen is 16 plus 2 hydrogens 18. So give me, who's got a calculator? Tell me what is the number of moles in 1,000 milliliters of water or 1 liter of water? 55.6. 55.6. All right, so it's 55.6 moles divided by what? 1 liter. So what is the concentration of water? 55.6 moles. Did you get it? So you should be able to do calculations like that all the time. All right? And if you're not sure, your strategy is always go back to the definition. You know, if they say concentration, then you say, what is concentration? Moles divided by the volume. Okay, let's pick a volume. Can I figure out the number of moles? So how do I figure out the moles in 1,000 grams of water? And so stepwise, you can figure it out. Okay? So now, from now onwards, you need to know that number. What is the concentration of pure water? 55.6 molar. All right? Okay, so getting back to this. So this describes the process. So now I want to show you a picture of what that looks like. So what we're going to look at is, we're going to look at the dissociation of hydrochloric acid. So what we have is 55.6 molar concentration of water. So we have lots of water. Water is the solvent. All right? And into this, we're going to put just 1 molecule of HCl. All right? And what you're going to see is that the HCl is going to give up its proton to the water, to 1 molecule of water. Okay? So I'll play this video twice so that you have an idea of what's going on. So this is liquid water. And down comes 1 molecule of HCl. The green circle is chlorine, and the white is hydrogen. And did you see that? So in order that you are not confused by the millions and millions of water molecules, initially we show all the water molecules, and then we're going to just kind of fade the other water molecules and look at just that one event where you see the proton transfer taking place. All right? So here again, and I want to show you that the amount of water is in far excess of the molecules of HCl. So there you can see that HCl loses its proton to a water molecule, and you see the formation of a hydronium ion. All right? And then it fades away because the number of HCl molecules are so small compared to the great amount of water molecules that are there, because the solvent is in such large abundance. It's in such great amounts. So it's like you have water, concentration is 55.6. The HCl is like 10 to the negative 3 molar. So do you see the concentration difference? It's like 10 to the negative 3 versus, or 0.001 versus 55.6. So there's a hundreds-fold excess of water molecules if you look at the relative ratios of the two. All right? And so, again, keep this picture in mind, because this is what occurs at a molecular level. So you can see the HCl molecule here. There's the hydrogen atom on the HCl. And now you can see that it's being transferred to the water molecule to form hydronium ion. And then what happens is, remember I told you the reason that it's very difficult to pin down a hydronium ion is because they're hydrogen bonded. Now, one hydronium ion can transfer the proton to another water molecule and form a hydronium ion. And then that will transfer it to another. And so it's really hard to describe a hydronium ion because the proton's being transferred all the time from one water to another, but also because there's a big cluster of those, because each is hydrogen bonded to another. And so it's hard to describe it because it's actually a hydronium ion, hydrogen bonded to water molecules, hydrogen bonded to water molecules, hydrogen bonded to hydrogen molecules. So it becomes a huge cluster. All right? That's what actually describes a hydronium ion. Okay, so we looked at acids. Now, in the same way, you can have bases as well. So let's take an example of a base. So we looked at acid dissociation constant, and we said the equilibrium expression can be described like that. Oh, sorry. Let me get out of this. So we said that if we're looking at acid dissociation constants, that's what it would look like. Now we're going to move on to looking at bases. So just like acids, now if we turn to looking at bases, and let's look at an example of bases. And I'm going to take an example like this. This is NH2 minus. All right, so NH2 minus. And in water, you have water. And if you set up an equilibrium, now what happens is that this will pull off a hydrogen from water so that you end up with plus like that. All right? So if you want to write this in the form of an equation, what you have is you have NH2 plus aqueous. This is water. All right? And now in this process, the water is actually the hydrogen atom donor, so that you form NH3 plus OH minus, where the negative charge is on the oxygen. All right? So let's look at this. Now here, this is the proton acceptor, and therefore it will be the base. Water is the proton donor, so water is the acid. All right, so we're looking at now an example of a base, which is NH2 minus. And if you place NH2 minus in water, what you would see is that the water donates the proton. So now water is acting as an acid. Okay? Now this is for the forward reaction. So if I look at the reverse reaction, you can see that for the reverse reaction, this is the proton donor. And therefore this would be the conjugate acid. And this would be the proton acceptor. And therefore this would be the conjugate base. Got it? So if I want to look at the acid-base pairs, so if I say acid-base pairs here, you would see that one acid, usually you can write this in any order, but I think there is, it helps to have an order associated with it. And so I think it's helpful for students to write the acid form first and then the basic form, so that it just allows you to kind of keep track of everything. And so if you take NH3 is the acid form, it has the proton. NH2 minus is the basic form where it's lost the, so this would be the acid, this would be its conjugate base. If this is the base, then this would be its conjugate acid. All right? Similarly, we have water and OH minus. All right? So the conjugate acid-base pair here would be H2O and OH minus. The only difference between them is that this has an extra hydrogen, this has one less hydrogen. So it's the difference. This is the donor, this will be the acceptor. All right? And so these would be the two conjugate acid-base pairs here. All right? Now I want you to remind you that when you write these equations, it's very, very important to keep charge balance. Remember, in nature, you can't create or destroy charge. All right? So to begin with, on the reactant side, do you see that overall what is the charge on the reactant side? -1, because NH2 minus has 1 minus charge, water is neutral. So that means when you write a balanced equation, on the product side, you have to end up with 1 minus charge. And you can see that NH3 is neutral and OH minus has a negative charge. Do you see that? So that way you maintain charge balance. So if you want to write the general reaction for a basic reaction, so the general form of the reaction would be, sometimes bases are negatively charged. So if your base is negatively charged, we call the base B. If your base is negatively charged in water, you'll end up with this, giving you BH. So this will accept a proton. H plus and a -1 will give you something that's electrically neutral, all right, aqueous, plus OH minus aqueous, all right? Or if your base happens to be neutral, so let's say you start with a base that has no charge on it, all right? So if this is that, then this plus water will give you BH. Now remember, this is a proton donor, so it's giving this an H plus. So if you take something that's electrically neutral and add an H plus to it, overall what is that going to become? Can you see that? It'll be BH plus, all right? So this is going to take up an H plus, a proton, and so this becomes BH plus, plus OH minus. So this will be aqueous, aqueous. So do you see the difference between them? Some bases will be negatively charged, and so you have to maintain charge balance. So on this side, overall, everything has -1 charge. On this side, everything has to have a -1 charge. Now let's turn to this. On this, on the reactant side, this is electrically neutral, this is electrically neutral. That means everything that adds up together on this side has to be electrically neutral. So you see that this has a +1 charge, this has a -1 charge, so there is charge balance on the product side as well. So both equations have charge balance. And that's a good way for you to keep track, because bases can be negatively charged or it could be neutral, and you need to pay attention to that. Okay? Now let's take the second equation. This is an equilibrium once again. And since it's an equilibrium, I can write the equilibrium expression again. But now because we're dealing with a base in water, we put a subscript B, and we call this, what do we call this? If we call the other one acid dissociation, what do we call this? We call this the base dissociation constant. And the base dissociation constant would be products. So let's take the second equation. So that would be BH plus, concentration of BH plus, minus the concentration of hydroxide divided by the concentration of B. All right, and we do not include the concentration of water because you're starting with pure water. It is a solvent. Its concentration on the scale that we're looking at does not change, so the concentration of water is a constant. And we said that all the constants are put together. So that concentration of water is already included in the concentration, the Ka. All right? So we're going to stop there for today. And on Friday, we're going to start looking at water, the solvent, in greater detail. Okay?